Hi, welcome back. In this lecture, we will study the torsional loading of circular shafts. Let's start. Our main objectives in this lecture will be as follows. First, we will discuss the effects of applying torsional loading to engineering structures and naturally, particularly to circular shafts. And then we will learn that the type of stress in torsional loading is actually the shear stress. For this reason, we will determine the shear stress, shear strain and torque within a circular member which is subjected to some torsional loading. And we will learn how to determine the angle of twist of a circular shaft which is subjected to torsional loading. First, let's define torsion. What is torsion? Torsion is a moment that twists or deforms a member along its longitudinal axis. It is the twisting of an object due to an applied torque. And in this figure, as we can see, there is a rectangular bar. Actually, it's not circular, but it is a rectangular bar which is subjected to an external torque. And due to this applied torque, this rectangular bar experiences some twisting deformation, some torsional deformation. And the type of stress that develops in a member due to torsional loading is shear stress. Why is that? For example, here we see a circular shaft which is subjected to torsional loading and its three-dimensional torsional deformation is presented. This red arrow here represents the direction of the applied torque. In order to find the direction of the applied torque, we can use the right-hand rule. For this purpose, we curl our fingers in the direction of the rotation and our right thumb shows the direction of the applied torque. Before understanding why the type of stress encountered in torsional loading is shear stress, I would like to first underline the importance of torsion. Why should we study torsion? Because many machine parts are loaded in torsion in engineering, either to transmit power, such as a drive shaft or an axle shaft in a vehicle, or to support a dynamic load, such as a torsion coil spring or a torsion bar. And in engineering, again, power transmission parts are typically circular solo shafts or circular hollow shafts, because these shapes are easy to manufacture and balance, and the outermost material carries most of the stress. The torsional deformation is encountered in many engineering structures, such as flexible space structures, robot arms, helicopter blades, wind turbines, and here, for example, you see the three-dimensional twisting deformation of a wing, and here we see a generator turbine configuration, and we have a circular shaft connecting this generator and turbine. This generator produces some torque which is transmitted through this shaft to the turbine, and please note that this circular shaft is subjected to some torque, isn't it? For this reason, it is very important to understand and evaluate the effect of this torque on this circular shaft, and for example, what would be the angle of twist? What would be the effect of torque acting on this circular shaft? And today we will learn to evaluate and understand the effect of applied torque to the circular shafts. For this reason, the torsion is a very important topic in engineering structures, for all kinds of engineering structures that you can encounter. And as I indicated before, the type of stress in torsional loading is shear stress. And now let me explain the reasons of it, why the type of stress in torsional loading is the shear stress, and why the shear stress controls the design of torsional members. So the shear stress is very important, it's a very important concept when we analyze the engineering structures, the structural members which are subjected to torsional loading. In order to understand this, please look at this figure and visualize. Think of a round shaft as a series of discs which are glued together on their faces as presented here. Let me use a pointer here, a laser pointer. So as you can see, we have a round shaft, and we can think of this round shaft as a series of discs which are glued together on their faces. Now let's imagine that if you twist this shaft with the torque of T, the glue will be loaded in shear because the load is parallel to the face of each disc. And since the load is parallel to the face of each disc, this means that the type of the stress produced by this load is the shear stress. Because please recall from our lectures that we analyzed last week, if the applied load is tangential or parallel to the corresponding cross-sectional area, in this case the type of the stress is shear stress. So this is the reason why the shear stress controls the design of torsional members and why the type of stress encountered in torsional loading is actually the shear stress. Yes, as I indicated before, we will start with the analysis of the formation of a circular shaft which is subjected to some external torque as presented in this figure. And this is our circular shaft. Again, let me use a pointer, laser pointer. So this is our circular shaft. From the side, it looks like a rectangle, as you can see. So this is the side view. This is our circular shaft, and from the side, it looks like a rectangle. In order to help with the visualization of the deformation later, let us put some grids on this circular shaft. Please note that each of these grids can be considered as a rectangle with all four right angles, actually 90-degree angles. And let me draw a line here in order to indicate the initial position of this point on the surface of this shaft. And now we apply an external torque along the longitudinal axis, namely the axial axis of this circular shaft. And we need to know how this circular shaft will deform on this torsional loading. But first, let us make several assumptions. We will assume that during the deformation, the length of this shaft will remain unchanged, and the straight lines that I draw along the axial direction will remain straight, and the cross-sectional area of this shaft will remain circular, and we will analyze the shape of this rectangular shaft after the deformation now. Please note that after the application of this torsional loading, after the torsional deformation, each of these rectangular grids now became a parallelogram. As you can see, do you see the shape change? So now they become the parallelogram shape, and we know that this type of shape change is characterized by the shear strain gamma. Gamma represents the shear strain, and this phi represents the angle of twist. This line, red line that I drew earlier, changed its position from this point to this current point, and this is known as angle of twist. Yes, I would like to repeat this because this is important. The red line that I drew earlier on the previous slide moved from its initial position to this current position, twisted by an angle of phi, and this is known as the angle of twist. Now let's continue with the analysis of shear strain. For example, here we will analyze the shear strain in a small element. This small element is represented by this red rectangle. We will analyze the shear strain in a small element with sides parallel and perpendicular to the axis of the shaft and at a distance of rho from the center of the shaft here as presented. And please recall that when this shaft experiences torsional deformation due to applied torque, this a point which is located initially at A change its position to A prime, and this displacement, this angular displacement, is represented by phi. This phi represents the angle of twist. Now let's analyze the shear strain gamma, which corresponds to this angle. How can we calculate the shear strain gamma here? So we will apply our knowledge from trigonometry. So from trigonometry, we know that the shear strain gamma is actually the tangent of shear strain gamma is equal to this arc length AA prime divided by the length of AB, which is the length of this shaft L. However, we are dealing with small deformations. For small angles, please recall that tangent gamma is actually equal to gamma, isn't it? Which means that the gamma would be equal to phi times phi, the rho times phi. Rho represents this distance from the center of the shaft, the center of the circular shaft, this radial distance. Rho represents the radial distance. Phi represents the angle of twist, and phi times rho represents this arc length AA prime, and this arc length divided by L would be equal to gamma, because tangent gamma is equal to gamma, because we are dealing with small deformations, and for small angles tangent gamma is equal to gamma. Now we have obtained an important equation for the shear strain as a function of angle of twist. And the shear strain varies linearly. Since it's a function of rho, it varies linearly with the radial distance from the center of the circular shaft, and the shear strain is maximum on the surface of this shaft. C represents the radius of this circular shaft here. The C represents the radius of this circular shaft, and the maximum shear strain occurs at the surface of this shaft when we replace rho, which represents radial distance from the center of the shaft, by C. C is the radius of this shaft. In this case, the maximum shear strain here would be equal to C phi over L. And we can also calculate the shear strain as a function of rho, radial distance, and as a function of maximum strain. So as we see from this equation, the shear strain varies linearly with the radial distance rho, and we also know that the Hooke's law, according to the Hooke's law, the shear strain is linearly proportional to the shear strain. Please recall the shear version of the Hooke's law. According to the Hooke's law, there is a linear relationship if we are in the elastic region. If the material behaves elastically, if the material is in the proportional limit, then there is a linear relationship between the shear stress tau and the shear strain gamma. And G here represents the modulus of rigidity, which is also known as shear modulus. Since tau is equal to G times gamma, and this means that since the shear strain varies linearly, since the shear strain is a function of rho, this means that the shear stress tau is also a function of rho, and it also varies linearly with the radial distance from the center of the shaft. The center of the shaft is located at O. If you look at a cross section at a specified location X, it has a radius of constant c and arbitrary radial position, which is represented by variable rho. As we derived earlier, since the shear stress tau and radial position rho are proportional to each other, shear stress develops proportionally with rho, with the maximum shear stress tau max occurring outside of this shaft at the position rho equals c at the radius. Therefore, based on this proportional relation, shear stress at any arbitrary radial position rho divided by rho is equal to tau max over c. Tau max is a constant, therefore we can express the shear stress developed at an arbitrary radial position as follows: tau rho is equal to rho over c times tau max. The question is, what is tau max? We know that shear stress is force over area by definition. Therefore, for a differential area dA on this cross section, shear stress at this point multiplied by dA is equal to small differential force dF. We can calculate the moment caused by this differential force about O. This is equal to the magnitude of the force times the moment arm, which is rho, and that equals to rho times tau rho times dA. We can replace tau rho by tau max over C times rho as we derived earlier. When we integrate the differential moment about the point O over the entire cross-sectional area, this value must be equal to the total internal torsional moment Tx at this cross-sectional area. Please recall from the statics course. The integral of rho squared dA is the polar moment of inertia J. Therefore, we can derive that tau max is equal to Tx, which is the internal torsional moment at this cross-sectional area at location x, times C, the radius, divided by J, the polar moment of inertia. As a result, the shear stress tau at any arbitrary position rho is equal to Tx times rho over J, polar moment of inertia. And this is known as the torsion formula. And please also remember the polar moment of inertia of circular solid shaft and the circular hollow shaft. So you can use these formulas in order to calculate the polar moment of inertia of a solid circular shaft and a hollow circular shaft as presented in this figure. Now let's analyze the angle of twist in the elastic range. We know that the maximum shear strain and the angle of twist are related to each other through this equation. Tau max is equal to C phi over L. Tau max is the maximum shear strain. Phi represents the angle of twist. C represents the radius of the circular shaft, and L represents the length of this circular shaft. And if the material behaves elastically and if the material is in the elastic range, which means that the applied torque values are not very high, they are not very large, they are relatively small, the deformations are small, which means that the Hooke's law can be still applied, because the Hooke's law can be applied in the proportional limit, until the proportional limit. And please also recall the shear version of the Hooke's law. Tau equals G times rho, G times gamma. Tau equals G times gamma is the shear version of the Hooke's law. So in this case, tau max over G would be equal to gamma max, isn't it? Because tau max equals G times gamma max represents the Hooke's law. And now we can replace tau max by the torsion formula. Do you recall the torsion formula? Tau max is equal to Tc over J. Tau max equals to Tc over J is the famous torsion formula that you should remember. And when we replace, let me use a laser pointer here. Yes, when we replace tau max by Tc over J, gamma max would be equal to Tc over Jg. And since gamma max is also equal to C phi over L, C phi over L would be equal to Tc over Jg. And then we can rearrange this expression in order to solve for the angle of twist phi. Here we obtain the second important equation in torsion topic, which is related to the angle of twist. The angle of twist can be calculated by using this equation. Phi is equal to TL over Jg. As you can see, the angle of twist experienced by this circular shaft, which is subject to this torsional loading, is a function of applied torque T, the length of the shaft L, the polar moment of inertia of the cross-section J, and the shear modulus G. If we have a composite cross-section consisting of different materials or different geometrical properties, or which are subject to the different applied torques, in this case, the total angle of twist can be calculated by using this expression. The phi, the total angle of twist of this structure which is presented here, as you can see, this structure here, this shaft is subjected to multiple torsional loadings. The total angle of twist experienced by this shaft would be equal to sigma TILI divided by JIGI. You need to substitute the corresponding torsion value, the length of the shaft, the polar moment of inertia, and the corresponding shear modulus of each section. Sometimes they are made of the same material, then we will use the same shear modulus G. However, they can have different cross-sectional areas, which means that they will have different polar moment of inertia values. And these different parts, can also be subjected to different torque loadings. And you need to substitute the corresponding net torque values applied to each part. Now let's look at this example. First, let me read the problem statement. For the uniform solid shaft with radius of C at the cross-section shown, the internal torsional moment is T. Determine the radius of the core, C' of the material that resists half of T. So please recall that when we were driving the torsion formula, we integrated this small differential moment over the entire cross-sectional area and equated that to the total internal torsional moment. And please use a similar approach here. Now let's start. For this purpose, we will again define a differential area. This differential area has a thickness of d rho and it is located at a radial position of O. Therefore, the area of this dA, this differential ring, our element is a differential ring this time. Again, let me use a pointer. Yes. So please note that our differential area is this ring now. And the area of this differential ring is equal to 2 pi rho, its circumference, multiplied by its thickness, d rho. And we also know that, so this is our torsion formula, tau rho is equal to T rho over J. Tau rho is the shear stress at an arbitrary position rho. Please note that the shear stress is constant along this ring, along the circumference of this ring. Why? Because tau rho is a function of rho. And here, since we are at a constant position, which is represented by rho, the shear stress must be constant, and tau rho is equal to T rho over J. J is the polar moment of inertia, and you can substitute the polar moment of inertia of a circular shaft into this equation. Please also note that since we follow a similar approach, the differential shear force acting on this differential ring is equal to the shear stress acting on this differential ring, which is tau, multiplied by the differential area or the area of this differential ring. And here we replace dA and tau with the corresponding expressions that we have obtained here earlier. dA is replaced by this, we substitute this into this equation, and we also substitute this expression which is used to calculate the shear stress at an arbitrary position rho. Therefore, this differential shear force acting on this differential ring at this location can be expressed like this, and the differential small moment produced by this force is equal to this force dF multiplied by its moment arm, which is rho. Now I substitute dF, this expression, into the following equation, and now we integrate this dMO over this internal cross-sectional area, because we are interested in this internal cross-sectional area here. So when we integrate this differential moment according to the problem statement, this must be equal to the half of the torque, T, the half of the applied torque. So which means that when we integrate this differential moment from 0 to C prime, this must be the half of the applied torque. So when you solve for C prime by using this equation, the C prime can be as a function of C as follows. C prime is equal to 0.841 times C. Now let's continue with the second example. Here we have a composite shaft consisting of 3 parts. Let me first read the problem statement. For the shaft subjected to these applied torques as shown below, determine the absolute maximum shear stress. And it is not stated here, but please also calculate the angle of twist of the whole shaft, AD shaft, which is the angle of twist experienced by this whole circular shaft. Please also calculate this. The radius of AB part is 8 mm and the radius of BD part is 40 mm, which means that the radius of BC and CD are equal to each other. Now in order to determine the internal shear stress, the shear stress in each part, in the AB part, BC part and CD part, we need to determine the internal torque values in each part. And we have a cantilevered circular shaft. One side of the shaft is fixed, it has fixed end. Therefore, this fixed end exerts a torque of TA on this shaft, to the AB part. Please note that this support reaction, this torque reaction is represented by TA. By applying our force equilibrium equation, we can determine this torque reaction exerted by the fixed support A. And since this structure is in equilibrium, tau Tx must be equal to 0. We choose the counterclockwise direction, which is accepted as positive for the support reaction, which is torque TA. If the results yields a negative sign, this indicates that you need to reverse the direction of the support reaction. Nevertheless, the sigma Tx is equal to Ta minus 100, because 100 is in the clockwise direction, plus 60 is counterclockwise, minus 40 is clockwise, therefore negative. This sum must be equal to 0 because the structure is in equilibrium. Therefore, the torque reaction or the support reaction in the form of torque exerted by the fixed end A is equal to 8 Nm. Now we can determine the internal torque in the AB part by using this. Again, we apply the method of sections. For this purpose, we pass a section through the AB part. This will expose the internal torque TAB existing in the AB part. Again, sigma Tx is equal to 0 since the AB part is in equilibrium. 80 plus TAB must be equal to 0. From here, we determine that TAB is equal to negative 8 Nm, which means that it is clockwise. The internal torque in the AB part is 8 Nm and it is clockwise because it is negative. Now, let's apply the method of sections for the BC part in order to find the internal torque in the BC part. Because when we apply the torsion formula, tau equals Tc over J, we need naturally the internal torque values. We apply the method of sections. This will expose the internal torque TBC. Again, tau Tx is equal to 0. 80 minus 100 plus TBC. I always choose the counterclockwise direction because the counterclockwise direction is positive in terms of torques. And if the result yields a negative sign, this means that I need to reverse the direction of the assumed one for the assumed one. Again, sigma Tx is equal to 0. 80 minus 100 plus TBC is equal to 0. And from here, the TBC is equal to 20 Nm. Now I will apply the method of sections for the CD part. This will expose the internal torque TCD. I apply my torque equilibrium equation. Sigma Tx is equal to 0 again. 80 minus 100 plus 60 plus TCD is equal to 0. TCD is equal to negative 40 Newton meters, which means that it must be in the reality clockwise. The direction of the TCD, internal torque, in the CD part is clockwise and its magnitude is 40 Newton meters. As the next step, we can plot the internal torque diagram for each section as presented by this graph. The internal torque between A and B is negative 80. The internal torque between B and C is 20. And the internal torque between C and T is negative 40 Newton meter as presented here. When we analyze the internal torque diagram and the polar moment of inertia of each section, it is clear that the maximum torque, tau max, would occur either in the AB part or CD part. Now we will calculate them by using the torsion formula. Tau max is equal to Tc over J. T represents the internal torque, C is the corresponding radius, and J is the polar moment of inertia. So we substitute the corresponding values for the AB and CD sections. And when we substitute these values, the results yield that the maximum shear stress occurring in the AB section is equal to 99.5 kilopascals. And in the CD section is 398 kilopascals. So as a result, the maximum shear stress occurs in the CD section. Now we will calculate the overall total angle of twist of this whole AD structure. Since we have a composite structure consisting of different parts which are subjected to different torques, we need to calculate the angle of twist for each part, for the AB part, BC part, and the CD part, and then determine the total angle of twist value. But please note that you need to substitute the signs of torques. This is important because some of the parts can experience counterclockwise twisting deformation if the applied torque is counterclockwise, and the part can experience clockwise twisting deformation if the applied part is clockwise. Let's start with the AB part. So this first, again, let me use a laser pointer. So this first part represents the angle of twist experienced by the AB part. The internal torque applied to the AB part occurring in the AB part is negative. The length of the AB part is 1 divided by its corresponding polar moment of inertia J and the corresponding shear modulus of the AB part, which is 75 gigapascals. Now let's continue with the angle of twist of the BC part. The angle of twist experienced by the BC part or occurring in the BC part is presented by the second term here. The internal torque is 20. The length of the BC part is again 1 meters. The polar moment of inertia is presented here and its shear modulus is 26 gigapascal. It is counterclockwise, excuse me. Here it is counterclockwise. It's positive. And the angle of twist of the last part is clockwise. It's negative because the net torque the net internal torque existing in the CT part is clockwise. Again, we substitute the corresponding sign here and we calculate the angle of twist of the CD part. Phi dA represents the angle of twist of the whole AD shaft structure. I would like to again underline again and repeat again. This is very important. If the shaft is subjected to different several torques, then we apply the torsion formula to each segment separately before adding each segment's angle of twist. And this is the overall total angle of twist of this AD shaft. It is equal to the sum of the angle of twist values of each AB, BC, and CD parts. Now, please continue with the Obojovo assignment. Thank you. Bye.